welcome back to Entrance and Beyond. Hopefully, all are doing good. This is day 12 of my DSA series. Today, I'm going to be discussing another linked list question. So, I'm going to solve question number 19, which is removed nth node from the end of the list. So, the question states, given the head of a linked list, remove the nth node from the end of the list and return its head. So, basically, this is our first test case 1, 2, 3, 4, 5. So this is our input. It's basically our entire linked list. N is equal to 2. So we have to remove the second last element, like mentioned. Remove the nth node from the end. So this is the last element. So this would be n is equal to 1. This is n is equal to 2. We remove that element and return. Over here in the second test case, head is equal to 1, n is equal to 1. We only have one element. That is the last element. We can simply remove it. And in this case, head is equal to 1, 2, n is equal to 1. So we have to remove the last node. We basically get 1. And basically the constraints are given over here. So size goes from 1 all the way up to 30, node dot value goes from 0 all the way up to 100, and n dot value is 1, and it is less than equal to size. And follow-up is given, could you do this in one pass? So hopefully you understood the question. The question is quite straightforward. We basically have to remove the nth node from the end. We don't have to remove from the front. And I just want to recall the logic of deleting a node. So it's quite simple. We basically need two nodes for that. I'll basically show that. So we need a previous node and we need a current node. So what do? We make previous is next equal to current dot next. So we're going to take previous is next is equal to current dot next. So this basically points to 5 now. And then we can do current dot next is equal to null. So this basically doesn't point anywhere. This connection is broken. And then if you want to delete it from memory, you can remove it from memory. So that is all that we do. So we basically do two things. First, we do previous next is equal to current next. So let's say we use C for that. Current next, and then current next, it would basically now point to null, and then we could delete it. We could directly delete it. So that is pretty much the logic behind deletion, and that is pretty much what we're going to use in this question. So that was the logic behind deletion. So the brute force approach, you would say, is that we could just count the nodes. We could traverse again. We could have a previous and a current. We could have a previous and a current. We could traverse through this for the number of times that are required. So if the size is suppose SC and we have to delete the nth element or nth node from the end, we can just do size minus n plus 1, because suppose size was 5 and n was 2, so 5 minus 2 is 3, but we have to delete the fourth element, so that's why we're going to use plus 1. So that's one of the basic approaches, but that would need a two-time traverse. So once we would traverse to get the count, and the second time we would traverse for removal. So that is the brute force approach to this question. I won't be going into too much detail regarding that, but hopefully things did make sense. If it didn't, I'll just show a small visualization. We'll basically have a previous, and then we will have a current. Now over here, count is 1 since we're at the first element. Then what do? It's simple. We move current ahead, we move previous ahead, count becomes 2. So as we know, over here we have to delete 4, and we'd have that stored in our variable. So then after that, what would happen? We'd take count, we would basically take count, move that ahead, take previous, move that ahead. Now our count would become 3. Then after that, we're going to take count again, move that ahead, and then we're going to take previous, move that ahead. At this point of time, count is equal to 4. We have the required count, and then do that logic. Previous is equal to current dot next is equal to null, and then we are good to go. We have basically deleted it. So this was the first approach, and I just helped you guys visualize that approach. So now this was the first approach. Okay, that did make sense. Now we have a second and better approach. So in linked list, we have something known as a dummy node. So we can always take a node as a dummy node, and that node will basically point to the head. And why do we use this node? I think it would make a bit more sense if we look at the edge cases. Like if we just had, suppose we just had one node. In that case, previous, you can't really set previous to null. That doesn't make a lot of sense. So we essentially need a dummy node. And what the dummy node does is it basically helps in, I don't know, we can say the dummy node basically helps us avoid the edge cases. We can simply use that for that simple purpose. So suppose I take a dummy node. So this is basically a dummy node, and we can initialize a value to it. So suppose, I don't know, let's just take -1. Take -1, this is a dummy node, and we connect it to head. And now what do? We take 2 pointers. We basically take a previous pointer, and we take a current pointer like we did before. We can start both of them at this position. Now what the logic is, the logic says first we're going to move the current pointer ahead by n positions. So suppose n was basically 2, right? So we're going to move this pointer ahead by n positions, or n plus 1 position, since we're starting at W. So counter comes over here, count becomes 1, comes over here, count becomes 2, comes over here, count becomes 3. Correct? Count becomes 3. Now this has moved how many positions ahead? N plus 1 positions ahead. Or we can say, if we just look at the linked list for the time being, we're basically at the nth position. And what do we know? We know that previous must come over here. So now what do? We move both of them ahead one at a time. We move, now suppose we have this, you understood this, right? We move count ahead n plus 1 position because we're starting at dummy. Now we take this pointer and this pointer. We move both of them one position at a time. We move this over here. We move this over here. We move this over here. Or we move this over here. We move this over here. We move this to null. We move this over here, and we are done. And as you can see, our previous is at the node. Our previous, now we have the previous. You don't have to do anything. You do previous of next. Previous of next is equal to previous of next of next, and we have our connection. And then we can simply return dummies next, and simply return dummies next. That is all that we have to return. So why does this logic work? It's quite simple. Let's say we have a number line, just to make me understand things. Suppose this is a number line that we have. Suppose this is a number line that we have, and we have some positions in the number line. Suppose we have some positions. So suppose this is distance 1, this is distance 2, 3, 4, 5. Let's say the number line let's just consider 5 positions for now. Let's make the gap 1, 2, 3, 4, 5. Like over here we had 5 nodes, right? Okay, these are the 5 nodes. This is essentially the dummy. So what we're doing is we're taking one pointer and moving it ahead and n positions, and then we're moving the second pointer. So we can effectively say that since we have gotten to the n position, current has gotten to the n position, how much would previous go? How much or how far would previous go? That is my question to y'all. That is my question to y'all. So suppose previous starts over here and current starts over here. Now current goes n position. If we just consider this structure, current goes till the nth position, right? So the value of n is 2, but we go 3 positions ahead because we're starting at dummy, right? So we go 1, 2, 3. So what's the space that is left? We can say the space that is left would basically be this is basically index 5. So this is going to go ahead twice, and it's going to go ahead another time. Correct? It's going to go ahead twice. So it's going to go ahead 3 times, and then P eventually will also go ahead 3 times, and that is what we want. What should be the index of previous? Index of previous should be total size minus n. Simple as that. Total size minus n. So if C is already at n, we can say that it basically has to go what distance? Now suppose this distance. Now this distance, we can say that is moved n. Correct? This is 1, this is 2. It has moved n. And the remaining space, what would it be? You can simply say it's over here. It's basically 1, 2, 3 because we go till the end. We go till the end. We go till it doesn't become null. That is what I'm trying to say. We go till it doesn't become null. So you can say that this is basically our size minus n. So we can say that P also goes for size minus n, and that is exactly what we want. So that is pretty much all we did. So like in this case, you can imagine it like this. Okay, we start off over here. Suppose we started off at 1. Forget the dummy part. The dummy part simple. We just have to do one more traversal. So suppose we started off at 1. Started off at 1. So how many positions did you go till 3? You can say that we went 2 positions. Then how many positions till the end? How many positions till the end? You can say, let's see, we're already over here. 1, 2, 3. 3. So what can we say? We can say that this pointer, this flow pointer, how many positions did it go? It's gonna go 3. So 1, 2, 3. And that is all that we need. So this is the approach behind the question. Hopefully it did make sense. I'm going to write the code. I won't show the brute force code. You can try yourself. I think that would help you all out. So what I'm going to do is I'm going to take this node star dummy, and dummy is just going to be a new list node. Dummy is going to be a new list node. Now is going to be -1. It's going to point ahead. And then what else do we need? We basically need this node star. And dummy is there. List node stars dummies there. We can take a slow. It's going to be set up to dummy, and then we're going to take fast. It's also going to be set up as dummy. So what's the logic? While okay, first we're gonna run a loop for int I is equal to 0. I is less than equal to n. We want to run it n+1 times because we're starting off at dummy. We're simply gonna do fast is equal to fast of next. Simple as that. And this won't go out of bounds based off of the condition. So it's always going to be less than size. This won't go out of bounds. Now what do? We simply do while fast is not equal to null. And some of you might be curious, like, why isn't this two path? It's not two path because we're only going to through the linked list once. So I should say this was just like a for loop. That's the logic behind it. So we can say it's technically a one pass big O of n approach. So while fast is not equal to null, simple, slow is equal to slow of next, fast is equal to fast of next. We are done. We have the pointer delete, so we can say slows next is equal to slows next. Next, we don't really have to make flashes next. We don't really have to change anything. Like, we don't have to make it pointer null, right? Because it's like we don't have to delete. That's what I'm trying to say. We don't have to delete. We're just gonna go through the linked list. For example, if 4 got deleted, 3's next would be 5 anyway, so 4 wouldn't get included, so we don't really have to do much for that. And what do we have to return? We have to return dummies next, which should always point ahead. Let's check it out. We take dummy is equal to new list node, -1 comma ahead, slow is equal to dummy, fast is equal to dummy. We run a loop. This runs n+1 times. Fast is equal to fast dot next, while fast is not known, slow dot next, fast is equal to fast dot next, slow dot next is equal to slows next, return dummy. Return dummies next because dummy is always is one element before our head, so it's just pointed ahead, and that's pretty much all that we do. And this works out. Hopefully this video did make sense. Do try the brute force approach and stay tuned for more. Thank you so much for tuning in.